So I would really like for this to be an interactive talk. I know that this is the last talk of the day, and you're probably feeling a little bit burned out. But please jump in with any questions that you have about us. This is really a story about our experiences. We have 4 colleagues sitting over here, or former colleagues, that are going to try and keep us honest in terms of what we're conveying to you in this talk. So I'm going to say again, hi. Hey. Awesome, great, thank you. Thanks for the introduction, Rob. I'm Owen. I am the lead consultant at Exertech Consulting. It's a consulting company that I've set up since leaving Enernoc, which is fairly recent. But while at Enernoc, I was a product owner and solutions architect involved from a very early stage of this startup company that we built up over the course of an 8-year period and sold to Enernoc, which is a public company based in Boston. So that startup is called Pulse Energy. I'm also the founder of a little company called Carbon Choices. I'm working on a social carbon tracker, tracking the carbon impacts of the day-to-day decisions that we make every day. But that's not what this talk's about.
Hi, I'm Nick Waller. I'm not sure if my mic is on, but I currently work as a site reliability engineer at Enernoc. My previous history is a variety of IT administration and operation roles. And in addition, I worked in some development roles, so that kind of brought me to a DevOps sort of beginning. Most recently, before Enernoc, I worked for a research university, the University of Northern British Columbia, helping to unite their developer and operations teams through DevOps. And that brought me to Enernoc, where, as I mentioned, I'm currently working as a site reliability engineer, working a lot with Chef and Amazon cloud services and CloudFormation-related technologies. And I'm on Twitter as Nick_Waller, so if you like anything you hear and you want to get in touch with me, Twitter is the best way.
Actually, I encourage anybody who is on Twitter, if you hear something interesting during the talk, please tweet it back to us. We appreciate it. Our Twitter handles are both at the start and the end of the presentation. Also, I should mention that this presentation itself is online. And I know that for the earlier sessions, it was quite hard to see the slides from the back. If you're having trouble seeing the slides, you can go online and follow along on your laptops or tablets or whatever as we go through the material. So this is a story of us over the course of the last 8 years, going from a monolithic Java application, several 100,000 lines of code that we built up over a 3-year period, to our current, calling it a polyglasm of microservices, about 15 different services being supported by 6 different applications, deployed in 3 data centers globally, so this is really a story about that journey. This is definitely a talk for those people that are into science fiction. There's a lot of 2001 references you'll get as we go through. So, how many people will own up to having built a monolith? Or having worked on a monolith? How about that? I mean, I'm expecting that everybody in the room should have their hand up right now. I was going to define what a monolith is, but A, everybody put up their hand, and B, I think the prior speakers today have already covered it in quite a bit of detail. But I think the definition of monolithic is a pretty good description of these systems that we have had the great pride in building. So for us, at the start of our Pulse Energy journey, myself and many of the other early members of the team, we had worked on monolithic systems in the past. This was not something that we were unfamiliar with. We had experienced the pain of working on a monolith, so we never really intended to build a monolith ourselves, yet somehow we ended up doing that. Anybody had that experience that despite the best of intentions and knowing that a monolith was going to cause you pains later on, you ended up inadvertently building one anyway?
What's the nature of software?
Is the nature of software. And so I've kind of scratched my head as to why we ended up in this position. And I think there's a few reasons which I'll get to in a second. But first, I want to point out some of the pains associated with working on a monolith. And given how many hands went up, I think most people should relate to this. So one is a term that I call code encumbrance. I'm not going to ask people to own up to having ever played Dungeons and Dragons before, but in Dungeons and Dragons, there's this notion of encumbrance, which is basically how much weight your character, your D&D character, can carry before they get crushed under the weight of all the stuff that they're carrying. And being a software developer, working on a monolith, I often feel the same way. You've got all this code weighing down on top of you, and how much of it can you really take? And once you reach that limit that's set for you as an individual, so you've exceeded your code encumbrance. Obviously, the cost of running regression tests against a monolithic system scale exponentially with its size. So if you notice that as you're doing coding and the cost of the amount of time that it takes to run a suite of regression tests against your system just keeps increasing, that's obviously a sign that you're heading in the direction of something that could be a monolith. If you notice that your deployments are becoming less and less frequent, partially because of the costs associated with that regression, that may be a symptom that you're heading towards a monolith. If you notice that you have certain aspects of your system that you would like to be able to scale, but you can't, or other aspects of your system that are relatively little used, but are now being over-provisioned, that is also indicative of this type of pain. Or if having a monolith, if any one aspect of that system goes down, causes a problem, causes the system to fail, you're down. There's very little resilience. And I think Matt covered this quite well, but if you've tried to have several teams all working together on the same code base, that also can be quite a big challenge. So how do you scale these types of monolithic systems is definitely a source of pain. So despite our best intentions, why do we end up creating a monolith anyway? Well, it was early days in a startup. We were launching a new product. It was in a new domain. We were analyzing smart meter data, making recommendations to building owners and operators about the operations of their facilities and how they could operate them more efficiently. And so it was new territory, and we were building up a system as quickly as we could. We also didn't know what aspect of our product was really going to was really going to resonate within the market, was going to lead to a lot of additional customers. So with that level of uncertainty, there's a real tendency to just kind of keep building on what you have. And I think that the visual metaphor is quite appropriate here, which is here we are as software developers working on honing and improving the monolith. Has everybody seen 2001: Space Odyssey? Okay, so the monolith, that black oblong object that you see in there is the monolith from the movie. So just a general question for here. I'm assuming that most people have some level of software development experience. If you have a simple function where you've got HAL, so HAL is the computer, the sentient computer from the movie 2001, you need to make HAL do something else. So HAL knows how to respond to a status check with affirmative Dave, knows whether or not it's time to leave the planet. So it's dangerous to remain here. You must leave within 2 days. So and as a catch-all, it says, okay, well, I'm sorry, Dave, I'm afraid I can't do that. So if you had to make HAL do something else, what would you do? Somebody tell me what would you do to modify this code to make HAL do an additional thing? Sorry, there are a few responses. How about you, sir?
I would say just add another else.
Yeah, you just add an additional condition. And you add an additional condition, and you add an additional condition, and you add an additional condition. And so sooner or later, it's very easy to follow this pattern where you just keep, you follow the pattern that has been established before. Michael Feathers, who wrote the excellent book, Working Effectively with Legacy Code, if you've heard of it, he noticed this and called it the canalization of design. So we noticed that as stream beds form from little bits of water, carving out deeper and deeper canyons that end up redirecting the flow of water, you see the same sort of pattern apply within software. So the early decisions that you make on a software project in terms of laying down some early design patterns are subsequently followed and followed and followed. And so that pattern becomes self-perpetuating. And we have a tendency to follow the path of least resistance. So, and to me, these are systemic problems, and this is part of the reason that monoliths are often inevitable without direct action in order to prevent them. So I think the advent of better tooling makes counteracting this effect significantly easier. So most systems grow through the accretion of new functionality. It just gets layered on and layered on and layered on over time, and before you know it, you're like the frog in boiling water, and you've just boiled yourself to death and built a monolith, to mix some metaphors. And before you know it, you end up with a big ball of mud. In this case, it's a dung beetle rolling what is actually a big ball of shit. Not to say that there was anything wrong with their code, it was all beautiful. So, but I think there are actually a number of good reasons why organizations build monoliths aside from following the path of least resistance. I mean, one is it's simplicity. You've got one system to reason about. At least early on, it's much easier to think about. If you're in a new business domain, where are the boundaries around that business context? It's not typically obvious at the start. And there's a fear that if you slice things incorrectly, or start to partition your systems in an inefficient way, then there'll be performance problems, there'll be scaling problems, so you'll have to make changes in both systems all the time. They're basically coupled together. There's an anti-pattern, which we mentioned later on in the presentation, called the dangers of the distributed monolith. So figuring out what the right seams are is not a trivial problem. It never feels like it's the right time. Like, when is the right time to say, okay, we're gonna stop building functionality here and we're going to create something entirely new, recognizing, especially if we've never done, other than building up the system the first time, we've never actually built a new system alongside it. There's a ton of design decisions, which we'll come to in a second. So that's ambiguous. Matt talked a bunch about Conway's Law. Most monoliths, I think, are built by single teams, right? I mean, that's where we started. We had one team, one system. We built and we built and we built, and then we had a monolith, and then we needed to split, and then you have problems. So it's quite natural for one team to be responsible for owning one thing. It's just when it grows too large, we've got a problem. And so then there's lots of barriers to being able to make a decision to move towards more service-oriented architecture. So there's deciding what technology to use. So we made the initial decision that we were going to build our application in Java. We knew that was not actually the best language or sets of frameworks for us to use to build an application. Well, we wanted something that was going to be allow for very fast iteration speed. Java is designed for stability. It's not designed for rapid iteration. But what's the alternative? When we started, Ruby and Rails were fairly well established, but there were all kinds of scaling problems on Rails. And I don't know how many people have put up their hands having built a monolith before. But how many people built a monolith on Rails? Because Rails is very easy to build a monolith on. It kind of encourages monolithic development. So it wasn't clear what technology, we knew we didn't want what we had, but what technology should we switch to? Then there's the question of shared code. So you've built up a whole bunch of functionality, maybe some shared libraries. How are you going to share that with this new service? Are you going to have to write all that all over again? What about versioning? So how do we ensure that service A is talking to the right version of service B and versioning the messaging that's used for communication between them? Now, instead of having to write the deployment code and infrastructure to support one application, we now have to do it for two or more, etc. What is the appropriate messaging format? Are we going to use SOAP, God forbid, HTTP with RESTful service endpoints, protocol buffer, thrift? So there's all these decisions that need to be made about adding a new service, and part of the promise of microservices is this suggestion that you can choose a language framing tooling that is most appropriate for the job. But what's that? It's not necessarily obvious. We all know Java. We don't necessarily know Node. And then there's performance considerations. So now, anytime we want to do something that requires that spans these different services, we're incurring the cost of network communication. So picking the wrong service point boundaries will cause all kinds of problems. So what's the alternative? We knew we needed to make a change. Well, so alternative number one, which I think is really where most people start. It's like, okay, well, we've got a monolith, so let's take that monolith and let's carve a piece out of it and turn that into a new service. So this seems really straightforward, right? I mean, all we need to do is take that bit of code that we've identified, that set of functionality, that module, pull it out into something else, package it up as a service, deploy it, and we've achieved our goal. How many people have done this? Right? How easy is that? So it seems really easy at the outset. I mean, intuitively, like you even if you look at the structure of your code, you look at it and you say, okay, well, this seems to be really separate from everything else, so I should just be able to pull it out and treat it on its own. But really, once you start to dig into it, you have something like this, which is you have a web of unexpected interdependencies that make doing this extremely, extremely hard and often very, very expensive. Depends on the size of the monolith. If the monolith is quite big, then this is going to be really, really quite hard. But it is definitely one path, and it's the path where we started. And there's a technique that we developed, which I call test-driven decoupling, which is using unit tests in order to enforce package structure so that you can use unit tests to specify rules about package interdependencies within your code so as to ensure that your understanding of how the code is structured actually is reflected in the code, and B, because of the fact that recognizing that this type of a decoupling exercise will take a while, you want to ensure that you don't backslide. New code changes should not go and undermine the decoupling work that is occurring. So I have a separate talk on this test-driven decoupling, but I'm not going to get into it today. But I think it's a really interesting topic. It helped us significantly restructure the monolith. It did not actually, for us, lead to the ability to pull pieces out. I mean, more often than not, you don't have the time or the budget to go and rewrite significant portions of your infrastructure. It's just not a cost-effective use of your business's money. And especially being in a startup context, like where you really recognize, where your paycheck is coming from, and it's not being used to go and rewrite a whole bunch of code. Please.
Also, how do you make sure that the new thing that you separated works the same as the old thing?
Yeah. there's that as well. Is it really worth it? So the second alternative, which initially seems a little bit counterintuitive, but I've found is much more common and is often simpler, is just to start by writing a new service. So that way you aren't coupled to the old system in terms of the technology decisions that were made, the frameworks that were used, the APIs that were established. You just start from the outside, write a new service, have an API for the monolith that old service will talk to. You can have the two running alongside. There's a pattern that's known as the Strangler application, which is that if you, and it's used within the context of talking about system rewrites. So instead of trying to take the big bang approach of if you have an existing legacy system that you're looking to replace and you write a new system alongside, and then you expect that you can just flip over to the new system and everything is magically going to work, yeah, that doesn't work. So the idea with the Strangler application is to identify certain new aspects of functionality that you want to add that aren't supported within the legacy system, bring that up and online, talking to the old legacy application, and then over time start to move functionality or implement functionality in the new application until it's completely strangled out the old application. So eventually that old application will go away. The reality is you're going to be living with both systems for a really long time, but that's one approach to take. And that was kind of where we thought we would go. But the reality is we actually ended up with more what I call a hub and spokes architecture, which is where that hub, so this is our life-sustaining systems are still there in the monolith, and then we have a set of services and applications that have all been built around it. And that's, I think it's actually, that I think was the correct decision for us. It does mean that you can spend a lot of time focusing on leveraging what you've got, and basically all the new development as much as possible happens outside of that in microservices and new applications that you build around that platform or monolith hub. How many people have experienced one of these patterns that I talked about? So either pulling systems apart, writing a Strangler application, or writing new services alongside. Yeah. So, and of the three, I'm just kind of curious to see which is most common. So how many people have split the monolith? And how many people have written a Strangler application? Okay, couple. And how many people have done this hub and spokes type model? Okay, interesting. So it's actually pretty split. Now I'm interested to hear some more of your stories. So okay, so how do we get from the monolith to this microservices nirvana that we're headed for? So first, a bit of guidance. This is a great book. It wasn't. So Sam Newman wrote this Building Microservices book. I think it came out 2 years ago. So this was well after we were well down the path of implementing microservices. But it did, it reinforced what we were doing. And if you are just embarking on this path, I recommend checking it out. So I'm going to pass things over to Nick now. Nick is going to talk about our recommendations, some of the lessons that we've learned from this process.
All right, thanks, Owen. I'm going to share as Owen says, some of the experiences that I've lived through, some of the lessons that I've learned, largely from an operational perspective. We're going to talk a little bit about technology choices, choosing a language or framework that makes asynchronous communication easy. Asynchronous communication in a microservices architecture is fairly important. If you have services that are depending on each other in an RPC style, and they're not getting response as quickly as they would like to, you might see some failures emerging. Owen, did you want to add anything around asynchronous communication or choosing a language or framework?
Absolutely. So one of the big things for us was we switched on to Node.js. So this was 4 years ago that we started building services in Node. So this was well before Node you reached this tipping point where it's at currently, and it was web scale. It was seen as new and experimental, and but we wanted to pick an alternative technology to Java, and it did prove to be a really good choice for it. But often when people first encounter Node, they hear about how it's like, okay, JavaScript is running on the server, so that means that you can share code between client and server. And that's often mentioned as being one of the main benefits of Node. That's totally not, to me, the main benefit of Node. So the big benefit of Node is that it's inherently asynchronous, so all the libraries, all the core frameworks are designed to support asynchronicity, and that you can natively consume JSON. So with JSON being the de facto standard for inter-service communication, the fact that you don't have an impedance mismatch between the message coming in and the code that can execute on that message is really, really nice, because otherwise, working in other languages, you're constantly transforming incoming messages into code and acting on it. Being able to act directly on the message is really, really handy. But in a microservices model, you're normally talking to, like, each service call may fan out to 5, 10 different backend services, and so being able to make all those calls asynchronously in parallel in a very simple way is great, and Node really excels at that.
Yeah, we've definitely found that Node.js is really great for asynchronous processing, but it's not a panacea either. It doesn't free you from having to understand how the event loop works. When you're using Node.js, it is important to understand the technology that you're using. If you have a route that's going through the application that's an expensive CPU-consuming process, and the other is a health check that you expect to return in a few seconds, if you don't have an understanding of the event loop, that can actually bite you. So asynchronous processing is very good, but you also have to understand what you're using. Dark side of polyglot?
Right. So one of the promises of microservices is that you are not bound to a specific language or technology. So as a result, you can choose the language that is most appropriate for the task at hand. So if you're doing something that's really analytics heavy, then maybe you want to do it using, let's say, Julia. And you have something that's very messaging focused, maybe you want to do it in Erlang or Elixir. And you have something that is working with financial data, maybe you want to do it in Java, Fortran, I don't know. But it's very, this kind of polyglot promise seems very attractive from the outset, but I think increasingly as teams have embraced the polyglot approach, they've also experienced the problems associated with it, which is that the reality is that the vast majority of software developers can really only be proficient at 1 or 2 languages concurrently. I mean, where proficient is, you want those people, like they have a detailed understanding of the current state of the art, et cetera. And there's going to be churn within your organization, and so that one person who was the Clojure expert that you hired is no longer there, and now you've got a service that was written by them in Clojure, and nobody understands how to maintain it. And I mean, in theory, with microservices, there's this idea that services are disposable, and they're small enough that you could just rewrite if you need to. But the alternative is to instead just come to terms with the fact that if you're choosing a new language or experiment, or a new language or framework, it should be recognized as an experiment and planned appropriately, and there should be some plan associated with dealing with the with that uniqueness, because otherwise you end up with Conway's Law all over again, where you can end up with teams that, like, your system is organized around teams that understand a specific language. So right now I'm working with a client. Their system was built by 3 technical founders, 1 knew Ruby, 1 knew Java, 1 knew JavaScript. And so today, now that even though they've grown significantly, they still have teams that are organized around those technology stacks, but those technology stacks are not necessarily aligned with their business value streams. And so as a result, anytime a new bit of functionality needs to be added, it needs to go through those three teams instead of having teams that are full stack that really own a value stream. And so again, Conway's law comes back into play. But that's enough about polyglot.
I want to expand a little bit, not even expand, just kind of add my comments to Owen's here. Who here has heard of kitchen unitaskers? It's anybody? No?
No.
Okay, the idea is you've got implements in your kitchen, your physical kitchen, that are really good at single tasks, like removing seeds from a watermelon. And that's really great if all you want to do is remove seeds from a watermelon. But if you get so many different tasks and tools that you can't keep track of all your tools anymore, that starts to become a burden. And that's why it's important to have appropriate tools, but you don't always want to have the most appropriate tools, because then you're trading for complexity and being able to choose those tools. Aligning service boundaries to bounded context and value streams.
So how many people have read Eric Evans's Domain-Driven Design? So it's a fantastic book. It's quite dense, but while a lot of the focus of people encountering the book are some of the earlier material around things like ubiquitous language or entities versus value objects. The notion of recognizing bounded context for systems is really important. And so there's a ton of great insight in this book, and the stuff that I was just mentioning about trying to align service boundaries with business value streams is key.
Share nothing architecture and monorepo versus repo per service. If you have code that you're sharing between services, that can become troublesome. You can end up with binary coupling between your services. So this is something that we did experience a little bit. We have shared libraries that we use between our different node applications. And that leads to deployment issues sometimes, because as you change your shared code, then you need to redeploy all the applications that use that shared code. And that starts to break down the walls between the microservices. It also causes problems because you're deploying all of your things at once, and you lose those benefits of microservices in their independent deployability and in their separation. It also makes versioning a little bit more tricky.
We were also talking about, and this is I think still an active debate within the company about if you do go with a microservices approach, do you also try and encapsulate each service in its own source code repo, or have one repo with all your code in it? And the node community leans towards one repo per module, which is the path that we took in following the guidelines that were established by the community. But it means that traceability for changes that occur across services, which are not infrequent, is harder to achieve. And if people have been following the source code structuring decisions for companies like Facebook and Google, both of them are proponents of the monorepo. So my understanding is that at Google, almost all of the source code that they have, which is tons and tons and tons of source code, I can't. There was some statistic I read recently about just the staggering amount of source code that they have, is all housed within a single repo. And so it's a single place that you can go, any developer can go and see any aspect of almost any of the systems that they have. Other than, I believe that the details of the PageRank algorithm is kept closely guarded and is not in that repo, but almost everything else is in that. And for exactly that reason, that it allows them to have visibility through the source control history about all changes, and then refactoring across services or upgrading dependencies across services all occurs in a single location. So it's it's a preferable approach. It's not the approach that we took, but it's an approach that I think the company's moving towards. Yes?
Does the deployment process play a role into choosing them?
It can, but it need not. But though I think that the choice of source control technology does play a role. So we use Git and GitHub. And Git is, while there is now support for sparse checkouts, it's not super well supported. It wasn't really part of the original design. Google uses Perforce, and well, they did use Perforce. It's a heavily customized version of Perforce, but it is well suited to just being able to check out subtrees. So you don't need to check out the entire Google code base anytime you're making a change. And this was actually one of the motivations for Facebook adopting Mercurial over Git, was that it does have better sparse checkout support.
Could you please elaborate on the danger of shared libraries? Because my understanding is that you break microservices in the right way. It's not a domain or domain code you're sharing for the data contracts and low-level stuff, right?
So that's true. But well, if it is, let's say it's shared messages or shared contracts, you don't necessarily, you may want to maintain backwards compatibility. You may not want to upgrade all services at the same time, or release them independently. And so centralizing that shared knowledge in single repos is great from the perspective of code reuse. But the coupling, it has to be evaluated against the coupling costs that are associated with it. So while it's something that we did, I would recommend trying to really minimize the amount of code that you own that is shared across these services. Unless it's, yeah.
But can you clarify what do you mean by library? There are a lot of node libraries, but they just come with Node.
Yeah, so that's a little bit different. I think it's more the code that you own and have to maintain that is more problematic. Obviously, you need to keep a close eye on the dependencies that you're bringing in as well. But it's more if, let's say I've got code that is in a shared module that is used by service A and service B, and I want to be able to make a change to that shared module. I need to be aware of what the impact is going to be on both services.
So that module itself is not a service?
It's not a service, no. So this is a library of, maybe it might be common utilities, but it's at least the way that we have implemented it is there are common objects, which are where the implementation is shared across services. I think in cases where they're value objects, it's a bit less of a problem. But if in the case of shared entities or structures associated with entities, it's a little bit more problematic. But it's just something to be aware of, is the amount of shared code between services and really trying to minimize it. That's the general recommendation.
I'm going to add to Owen's comment, and there's a question over here. Specifically in the case of client libraries, if you're representing objects in your domain with objects in a specific language, and you start putting too much intelligence in that client library, you can run into a situation where you've put some intelligence in for a specific language like Node.js, and then if you have a different language that's clearly a better choice for solving a problem, you might have some resistance to be able to adopt that because you've already invested so much in the client library for Node.js. There's a question over here.
It was about the shared libraries. Wouldn't proper versioning of these libraries mostly fix that issue?
The versioning definitely helps. It's more just kind of an awareness of where these different modules are being used and what the impact is. So most of the time when you're bringing in third-party dependencies, they have fairly well-specified APIs. But in a shared library, we're not necessarily as diligent about about what the APIs are, and so, yeah, just something to be careful of. Oh, sorry, that was my laptop going to sleep. Too much talking, not enough slide progression. Oh, actually, no, it's more than going to sleep. All right, let's try this.
Okay, great. Integration between your services. How do you do it? If you don't know the answer to that, you probably, for the start, want HTTP RESTful services. And that works great until you start running into problems. Like, let's say you have a service that does some computation, and when you have a small data set, it takes 1 second, and then later it takes 5 seconds, okay, 10 seconds, 300 seconds. Ooh, now you're getting into some trouble. Because your HTTP request runs through typically a load balancer. How long does a load balancer let the TCP connection last? Well, 300 seconds is common on Amazon. So if you are using HTTP RESTful endpoints for your integration between services, and you're doing heavy computation, you'll run into big problems as soon as it runs past a certain scale. And so at that point for integration, you might look at message queues, queuing as an integration point. Safety through isolation and compartmentalization. Here's an interesting story. So with the software that we were working with, we have 2 main use cases. We've got users coming in from the web, and they want the pages to load really quickly. And we also do batch jobs, big report generations. And these are extremely computationally expensive. They work on very large data sets. Both of these 2 different use cases that have very different performance characteristics rely on the same services. So if you run them at the same time, you don't get quite what you want. You run a big batch job, and these services are all tied up with like 100% resource utilization, which is great, unless you want your users to be able to view your website. So something that we had to focus on was isolation and compartmentalization. Within an environment, we would have different deployed blocks of services, and these blocks would serve different customers, basically. We'd have a block for serving the users on the web, and we have a block for serving the reports. And these bulkheads are a really important part of us being able to maintain stability and availability of our microservices, while still, like, we keep good latency that way because we have some dedicated to just having a low latency response processing. And we also get to increase our resource utilization because we can have some of our services running at 100%, and it doesn't matter how quickly they have to respond.
Don't both of those share the same database?
They do share the same database, that's correct. If you run into problems with performance on the database, you might want to consider that is definitely something to worry about, for sure, you're right. That's something we haven't encountered very much. Most of the problems we had were like the database answers quickly, and then we do a lot of computation in our microservices. Yeah. But that is actually a great point, is you have to worry about performance and database contention as well. Question in the back?
Yeah, so you're saying blocks of services, that blocks of instances that execute a given service, and some are reserved for interactive jobs, low latency, and other instances are reserved for potentially higher latencies out.
Yeah, so specifically how we're doing that is with ELBs, Elastic Load Balancers in Amazon. We have one service deployed within an environment, but it's divided into different blocks, and each block has a different load balancer. So then the other applications that consume it are also divided into each relevant block, and then all the microservices within one block will only make queries to load balancers for other services within that block.
So the endpoints are slightly different. Yada 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 fast, yada 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 slow, or something like that. There must be some way to specify which block you're going.
Yeah, we actually use the same name for the endpoint because it's important to us to be able to specify that in the configuration files and within the application. Then we just use some DNS hijinks to return different results depending on which block the node is existing in. Deployment, I had alluded earlier to some deployment issues and deployment clustering. One thing that we've seen a lot, especially with the introduction of microservices, is our build agents get really busy right around 4:30 as people will finally push their changes to code, especially shared code between services. So now we build the world. Owen, did you have anything you wanted to add to that?
Well, one motivation that I've seen for switching away from a monolith is the build takes forever, right? You've got a lot of code that is building. You should really only rebuild and re-release what is necessary for a given change. And so initially, switching to microservices architecture is great because you've got all these small services that build quickly and they only build when necessary. The problem is if you do have these types of shared libraries and somebody goes and makes a change to the shared library, then that's now triggering many dependent builds. And then off the builds, we have we do automatic deployment. So continuous deployment is fantastic. We deploy continuously to every environment other than production. So that means as soon as a developer commits a change to a given service, then that service will be immediately pushed into each of the non-production environments. So that's the test environments for each data center. The user acceptance environment is also a bit controlled, but that's great, except for the fact that you now have this massive fan out of builds that are happening concurrently. So it doesn't mean you just need to scale the number of agents that you're running. For us, all this infrastructure is also running in the cloud, running at Amazon EC2. And one prerequisite, I would say, for being able to do continuous deployment is to have a zero downtime deployment environment set up. So there should be no visible impact to the deployment of new services. I mean, effectively, they're happening all the time, which is great because that means that you are testing your deployment process all the time and you're verifying that the impact on your end customer is going to be invisible each time new deployments happen, because the same environments that you're using for testing are being continuously deployed to. Igor.
You mentioned that you deploy to a non-production environment on the change.
Yep.
Is it branch specific, or you're assigning environment per branch, or you're not using branches?
So the question was about branching and continuous deployment. So the way that the team works is that all development happens on master. So master is what is being monitored for changes, and those changes are being pushed out to the different environments. For patch releases, which do happen, every time there's a production release, that version is tagged and a branch is automatically created, and there are build targets for the patch branch. And that means that changes that need to go out to patch can be merged up to the patch branch and then deployed separately.
So feature branches are not deployed.
Feature branches are generally not used. So there is feature branching happens when changes do have to happen in isolation, but it's the rarity rather than the norm. So I know there's definitely a trend these days to do branch per feature, but that's not something. I think the jury is still out in terms of the approach. Part of it depends on the team and what approach the teams are most comfortable with. To me, one of the main advantages with branch per feature is that it may encourage a code review process that might not happen otherwise if you're requiring somebody else to merge changes into master before deployment. But won't get into that discussion.
I do want to get a little bit more into continuous deployment. This works really well for us. We continuously deploy to test. So when somebody makes some code that causes a problem, test breaks, that's great. Now we know about it before it's in production. But who here has heard of 12-factor, the 12-factor application? Only a few? you're all interested in microservices and agile, I would encourage you to go look up the 12-factor application. I'll just take a moment for anybody who wants to write it down. Okay. So one of the factors in 12-factor is about keeping as much parity as possible between dev and production and test and production. And so what we're doing right now with continuous deployment where feasible to test, but not actually continuous deployment to production, sometimes is a little bit troublesome. So if you commit change A to service A, and that works great, and then you change service B to consume that new feature in A, and that works great, then you release service B, but service A hasn't been upgraded in production yet. Now service B in production is failing, even though it worked properly in test. And that's why it's really important as you're building out a continuous deployment system to really try hard and minimize the latency that changes sit around in test. You want to get that parity as close as possible together. Provisioning. So we're actually using Chef to sort of deal with that problem right now for provisioning. For each of our microservices, we have a cookbook in Chef, and Chef allows you to specify metadata dependencies between applications. So when you modify an application that changes the configuration or offers some new features, you might bump the cookbook version. And then the cookbook of the application that will depend on it, you can set a dependency in there that says, well, I'm good up to this version. So that when Chef tries to run in production, you say, oh, right, I need to release this other application first. One of the patterns we've seen work really, really well for us with Chef is extraction of a common cookbook for similar languages. So for Node.js, we have a cookbook. And anytime you want to deploy a new Node.js application, instead of writing a whole new cookbook with all of your deployment scripts and everything that you would have, you just reuse this one Node app cookbook and allows you to get microservices out much more quickly. So, we've done similar things for Python, for Ruby.
This was a really big win because this means that, going back to the earlier part of the presentation, there's this inherent cost associated with introducing a new service. But by standardizing the cookbook for provisioning and deployment of a service of that type, so it's got all of the monitoring in place, all the security infrastructure in place, it just makes it so that creating a new service is adding only a few lines of code. It's really filling in a few placeholders. And it ensures the consistency in terms of the services that you're creating, especially in terms of the infrastructure that they use.
Well, to a certain extent, Chef becomes kind of a snow globe world where you see the same problems with microservices echoed again at a smaller scale. If you have, oh, sorry, I lost my train of thought where I was going with that.
Maybe versioning.
It was with versioning. So if you have your services and you, do you want to carry on? I'm going to try and catch up.
Well, so dealing with having different services, you need to worry about the version of the different services. You've got the same kind of challenges when you've got now cookbooks per service and ensuring that that all of the deployment metadata that is associated with the specific version of service A is compatible with service B.
Yeah, that is a good point. Also, we had a discussion earlier about code reuse, and this is something we see in the Chef world as well. We just talked about the amazing benefits that we had with the cookbook for each language. But if you have a whole bunch of services built on a specific language that all rely on this particular cookbook, then when you want to change that one, it's a little bit like if you have a whole bunch of microservices depending on one service. And what happens if you want to make material changes, breaking changes to that one dependent service, that you get the same problems with a big microservices system as you do inside a Chef system, because each Chef cookbook really is like its own little application. The way that we control cookbook versions in our production environments, I'm not sure how many people use Chef here. A few, small number. So as I mentioned, each Chef cookbook is kind of like its own unique application. And Chef has the notion of environments, which allow you to pin specific versions of your cookbooks. So for our test environments, we don't pin those versions at all. Anytime we make a change to a chef cookbook, it just goes out. We get our continuous deployment that way into test for our chef cookbooks. And in production, we're a little bit more careful. We pin specific versions of that code. And again, it looks a lot like a microcosm of the microservices world. Chef is a smaller place representing that. I'd also like to mention containerization of runtime environments. This is a fun little story that we ran into a little while ago. Who here has code that depends on their customer's code? No? Nobody thinks they do? You might want to double check that assumption, because we didn't think we did. We had a tool, I'll call it the scraper, that would connect out to our client's computers, basically, and download some data, and it did so over a VPN connection. Well, the client updated their VPN server, and all of a sudden our client didn't work anymore. So without necessarily realizing it, our code had actually become dependent on our client's code, funny enough. So the way that we dealt with that is with Docker, because we needed to get a new version of the VPN client, and in order to do that, we needed to update to a newer version of Ubuntu, and that was going to be kind of a bigger deal because there's several services co-located on one server. But by using Docker and containerizing the service, which was really only took about a day, we were able to get the new version of the VPN client, get the application deployed, and it was back in production with the client never noticed. We still had all of our data intact. And that was kind of a turning point for us on realizing the benefits of containerization. Security and shared secrets. So you've got your microservices, and they need to talk to each other. In a monolith world, that's really easy. You have different parts of the program. You don't normally authenticate access between different parts of the program. But as we mentioned before, you're probably using HTTP, some kind of RESTful style interaction, and that traffic is going out. Maybe it's going over the public internet, and you want to protect that a little bit. You need some authentication. You've got your services that are exposed to the public internet. Maybe you have end users making requests, depending on what kind of service you're providing. So how do you do that? What worked really well for us is having simple shared secrets. Each instance of a service in an environment has its own secret that identifies it. So when it calls out to another service, it says, this is me, here's my request, and it signs that request by adding a header of its own shared secret. And then the other service can authenticate that. It can say, yes, I recognize you, service, by your shared secret, and I will accept and respond. Something important to realize here that we learned a few months back is on key rotation. So everybody here knows SSH, and SSH passwords are not as good as SSH keys. But why? Well, let's say you have your user and your server, and you want them to be able to always interact. So you change the user's password on the server, and they say, I can't log in now. Okay, well that won't work. So you tell the user their new password, and they log in, but the server is outdated. They say, I can't log in. Well, that doesn't work. You have this kind of one-one relationship, where if you change either one, it'll break. So you need to have some kind of intermediate. And that's why SSH keys are nice, because you can have two different keys approved on the server. The client connects with an old key, it works. The client connects with a new key, it works. And you can phase one out as you phase the other in. Shared secrets is something that we had here as well. And we ended up having to do it just like SSH keys. That your application should be able to look at an old secret for a client and say, yep, that's good, or a new secret and say, that's good. Anybody who uses Amazon and is familiar with IAM might be familiar with this. For each user, they can generate two different API keys, and that's so that you can phase out an old one as you phase in a new one.
Where are those secrets stored?
Where are the secrets stored? We would like to use a tool like HashiCorp Vault. We're not currently using a tool like that. So the secrets are stored in configuration files where the applications are deployed.
Under version control. But I guess part of what we wanted to point out here is that when moving to a microservices world, at least we had this kind of fear: do we need to implement SSO? Do we need to grapple with SAML or implement OAuth? And at least for inter-service communication, Shared secrets is just a very, very simple mechanism that can allow you to get up and going very quite quickly without needing to adopt one of these more significant frameworks.
Load balancers for backend services. Some of your services you'll be exposing to the public internet, to your public user base. Some of them will be internal. In a previous speech, the facade pattern was mentioned, where you have services which might take internal services and make them more presentable, more friendly for external users. Chances are you want to use principle of least privilege and take those internal services and not expose them. That lessens your security border. In Amazon, if you're using a VPC, you can do that with your Elastic Load Balancer. You can take an ELB and mark it as private, so it only serves internal addresses, or you can have a ELB and make it public. If you're not using a VPC, then you don't have that benefit, but everybody here should be using a VPC. Monitoring and health checks. So, who here has health checks on their applications? Okay, that's actually less than I expected. So we had a fun little scenario with backing services and health checks. If you have a service that depends on another service to fulfill requests, you ask yourself, does it make sense for my health check to fail if the other application has failed? It depends on coverage and code paths. So if your service can't do anything at all useful once that other service is down, maybe it's something simple like a database, and your service can't do anything if the database is down, then you probably want to fail your own health check. But under any other case, if you can still do some of your work, you probably don't want to fail your health check, because if you have a whole bunch of services that all do partial coverage, and you have one little thing that fails that wouldn't take down all of your applications, that some requests could still go through, but service A depends on service B, depends on service C, and service C marks itself as failed, so B marks itself as failed, so A marks itself as failed. Now all of your applications are dead, but even though they could still be serving some requests. So it's important to keep your health check, return true. Say you're in a good state if you can still service some of your requests, and for the other requests that wouldn't be serviceable, there are HTTP codes for that normally that explain why something is going wrong without necessarily failing it completely, removing your application from load balancers and causing more cascading failures.
One just further comment is we found it to be quite valuable to have all health checks accessible from a common URL. So if HTTP is the standard interface that all services speak, and so there's a common root that every service will implement, which is this _HC. So you know if you're trying to do any sort of monitoring across service, or even just trying to ping a service that you're not familiar with, you know where you can go to find out what the health is of that instance, and that they should all return information in a common way. So that being an HTTP status code, obviously, because that's what's going to be used by the load balancer, but a JSON response to provide ideally more detail. So if there are these interdependent services that it is reporting on, like that health check should give a status update on all those dependencies.
Question over here?
Yeah, what are some of the ways you handle those failures from a service that is running and that depends on that?
It depends on the HTTP code. You might, within your service, say, I'll probably be able to service this later, so you turn a code that says, try again in half an hour or an hour. You might not have that knowledge, depending on the circumstances. So you just say, server overloaded or server error. I'm not sure, have I addressed your question?
To some extent.
This health check, is it humanly readable, or is for load balancer to not serve request on this particular server, or is for alarming system like Android?
We actually use the same health check for all those different purposes. So the HTTP status code is what informs the load balancer as to whether this application service should still be within the load balancer. It's JSON, which for some people is considered human readable.
At least it can be easily transformed into a format that is.
Yeah, and again, with our monitoring, the HTTP status code returns the state of that service, and we do keep in Graphite actually the history of all of our health checks returned. For other dependent services like backing services that would cause a service to become degraded, we don't keep that in our monitoring. That's actually the human readable aspect. So if you're investigating a service and wondering why is it in this bad state, you can look at the health check and see, oh, it's passing because it still wants to be in the load balancer because it can still do some work. But it's not in a perfect state, that some parts of it are degraded. And you see that in the JSON, and that's human readable. I mentioned about our Graphite. We also use the ELK stack. That's Elasticsearch, Logstash, and Kibana. How many people here use ELK stack? A number of you, okay. We use that for all of our log shipping. Generally, when you want to look into an incident, logs are really useful because you can find out what the context of the situation was. And logs are not really for alerting usually. That if you say, we'll discover the problem by reading the logs, then you won't discover the problem. Logs are for investigation, and we use ELK quite heavily for that. So we log quite verbosely to provide as much context as possible as we're doing our investigations. We use Pingdom for an external validation and of our service availability, and we use PagerDuty for alerting, largely based on Graphite metrics. And we do have a few checks within the ELK stack of certain log events that get logged. They can trigger notifications and PagerDuty incidents. Follows the microservices.
So those were the main recommendations that we wanted to provide. Obviously, microservices is not a panacea. It creates a lot of new problems for you. One problem which I alluded to earlier on in the presentation is this danger of building a distributed monolith. So setting inappropriate service boundaries so you have very chatty services that are all interdependent. You've basically taken that messy alien goo that I alluded to before and now just distributed it, in which case you're often better off just keeping it in one service because you're not going to realize a lot of the benefits of a microservices architecture. More builds and more deploys, we talked about that earlier, about the problems that creates. Cascading failures, it's now possible to end up in situations where you can have one service take down another service by inadvertently launching a denial of service attack. Nick talked about establishing bulkheads within our environment. That's one way to minimize the impact of the downstream impact of services overloading downstream services. But it means that from a provisioning and scalability perspective, you need to consider what the impact is not just for the service that you might happen to be working on, but also the downstream services. And at this point in time, there are more services than teams. There are not yet more services than people, but that's probably going to come about pretty soon.
Actually,
so the question is...
We just crossed that mark.
Oh, okay. All right. So the question is, who is responsible for a given service? One beauty of microservices is you may have a service that is running perfectly for untouched for 12 months, and it's great. I mean, who really needs to be responsible for it? It's basically it's taking care of itself until there's a problem with it, of course. What is the right way to apportion ownership and responsibility for services, especially as your teams change, as the focus of your organization changes? Your team might have built something up, a service up, but now they're focused on something completely different, and then being dragged back into dealing with the service that they're no longer really looking at. So these are some of the challenges. I mean, they would be there anyway, even within the context of the monolith. But both the pro and the con of the service is that it's encapsulated, so it can be out of mind. You put it out there in the corner, and not really have to think about it. But then if there's a problem, it may mean that nobody's really paying attention.
Do you have a formal ownership? Like particular person assigned to particular server?
Not on a person level. It's normally on a team level.
Yeah, so we've taken a little bit of a look at this, and there's not really any way to solve it by different team assignment or by person assignment, because basically what it comes down to is you're going to generate a lot of code, and you're going to generate more code than your entire team can maintain in their head. And that's why microservices are so appealing, is that you can take a service, if it's well-defined, and forget about it for 12 months, and use that time and space in your head to work on other things. And when you come back to it 12 months later, that if it was a monolith, you'd say, oh, wow, there's no way I can comprehend this. But because it's a microservice, you can come back, the borders are nicely defined, and load it back into your head and resume working on it.
That's an interesting way to define microservices.
No, it's
Please.
Do you use Agile?
Yes.
How do you map microservices to the Agile process?
In what aspect?
Is it user stories, one micro?
Oh, I see what you're saying. So, I think if I understand the question correctly, so let's say there's a new story, a new feature that the team needs to work on. Is there a mapping between that feature and the associated service? Is the story broken down at a per service level, for example? So I've seen different things. So at Internoc, that's generally not really done. I mean, the ideal is that the story represents end-to-end functionality. At other organizations, I've seen that. It kind of depends on who's driving the story definition process, and if it's being done by a developer on a team who is responsible for a specific service, then they might write that task or that story as being specific to that service. One way to think about it is where you could still take it within a story context is that the customer that they're delivering the story to is the team that's responsible for the upstream service. But the ideal, at least in my opinion, is that the teams are full stack end to end, and that the story defines that entire flow of work. The question is whether or not the team is capable of implementing that within the confines of an iteration. But in process-wise, I would say that the team is following a very agile, very lean startup influence process, but that is not explicitly one agile process or another. So it's certainly not Scrum. It's not exactly extreme programming, but it's a process that works and is very lightweight.
So that was a very good description, but how does the architecture play into that then?
How does the architecture play into what?
Into that process, so who decides what the service will be, and those stories that are agile, that go vertically,
Yep.
they don't answer that question. Somebody needs to be hired and that looking at the architecture.
So I think the architectural decisions are definitely come into play in terms of deciding on service boundaries. Once as the services are set, it's really up to the team responsible for doing the work to decide how to implement and deliver that functionality. At least I would say the way that the team works is there's not strong architectural oversight, but part of it is because there's a lot of very experienced people on the team that have worked together for quite a long time. And so that knowledge is quite broadly shared. For the most part, even though there is some degree of ownership or responsibility for certain services, the team practices collective code ownership so that different teams can make the changes to services, even services that they're not necessarily responsible for, in order to ensure that that end-to-end functionality is delivered.
So in your case, the team is responsible for the architecture.
Yes. Yeah. Is that a fair characterization?
I think we're not quite big enough yet that we've gotten to the point where that type of approach is not feasible. I think more or less that type of knowledge is still fairly spread out across the team.
So the product development team is about 40 people? 30?
Okay, but yeah.
Yeah, so that's including product management, testing, operations, development.
I'd say generally for a lot of our services, if we get to some weird sort of architectural question, there'll be a discussion amongst a few people. We'll figure out what the best approach is and move on from that.
And to me, that actually mirrors the microservices style, which is that it is a distribution of responsibility. It's moving to a consensus-based model. So,
I think that wraps up pitfalls for us.
yeah, and we should wrap up the presentation too. I think we're a bit over time. Thank you very much for all the questions, of course.
Future work, if you want to address anything on here, I did mention around containerization and the benefits that we found.
There's still lots of work to do, and there are lots of other companies that are further ahead in certain aspects of their microservices deployment. So, but that's it, I guess. So I think that's it. Thank you. Thanks for your attention. Thanks for your questions. And thanks to the organizers.
Thank you very much.